Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. My name is Sukamta, and I'm honored to present our research title Investigation of Two-Phase Flow Pattern of Glucose, Oil, and Liquid in a Horizontal Mini Pipe. This work was conducted by our research team from the Department of Mechanical Engineering at Universitas Muhammadiyah, Yogyakarta. Ladies and gentlemen, two-phase flow plays an important role in various systems, including biological systems like blood circulation, energy systems such as heat exchangers, and industrial pipelines in oil and gas transport. Despite its importance, two-phase flow involving glucose, oil, air mixtures in mini pipes is still rarely studied. These systems exhibit complex behaviors influenced by fluid properties, velocities, and geometry, making them a valuable topic of investigation. In this study, we aim to investigate the flow patterns that occur in glucose, oil, air mixtures, understand how viscosity affects the formation and stability of flow regimes, develop flow pattern maps for two different mixture ratios to support future microfluidic application. Ladies and gentlemen, our experiment involves a detailed setup that includes a pump, compressors, mixers, test sections, and a high-speed camera for visual observations. The working fluids were emulsions of 10% glucose and coconut oil with two volume ratios 7 compared 3 and 2 compared 3, stabilized using gum arabic. We carefully controlled superficial gas velocity and superficial liquid velocity to capture a range of flow pattern. Ladies and gentlemen, our results showed that the 7 compared 3 mixture exhibited a wider range of flow patterns including plug, bubbly, slug annular and churn flow. And the 2 compared 3 mixture displayed only plug, bubble and slug annular patterns. This indicates that higher viscosity in the 2 compared 3 mixtures reduces the diversity of flow regimes. In a plug flow, elongated gas bubbles are separated by liquid slugs. This flow was more stable in the high viscosity 2 compared 3 mixture and more fragmented in the lower viscosity 7 compared 3 mixture. Ladies and gentlemen, bubbly flow consists of small spherical gas bubbles dispersed in the liquid phase. It was most stable at low gas velocity and high liquid velocity. However, as GL or liquid superficial increased further, the flow became unstable. The high viscosity of the 2 compared 3 mixture also reduced bubble mobility and visibility. Ladies and gentlemen, in slug annular flow, a continuous gas core is interrupted by periodic liquid next. This flow became more stable in the 2 compared 3 mixture due to viscose damping. In contrast, the 7 compared 3 mixture displayed more turbulent behavior. Ladies and gentlemen, an annular flow was observed only in the 7 compared 3 mixtures. Here, gas flows through the center of the pipe, with a thin film of liquids along the walls. At higher gas velocities, the liquid films was further flattened, indicating stronger gas dominance. The two complementary mixtures, being more viscous, did not exhibit this pattern. Ladies and gentlemen, we created flow pattern map based on the superficial velocities G, and GL. The seven complementary mixtures showed five flow regimes, while the two complementary mixtures showed only three. This map provides a visual presentation of regime boundaries useful for predicting transitions and multi-phase systems. Ladies and gentlemen, when we compare the two vectors, the 7:3 ratio support a broader range of flow types, and 2:3 ratio due to higher viscosity shows limited regime diversity. We also compared our findings to a previous study using air glycerin mixtures and found our emulsions provided more defined plug and bubbly zone, emphasizing the importance of fluid selections in microfluidics design. Ladies and gentlemen, so our findings have significant implications in biomedical, chemical, and food processing industries. Understanding how viscosity affect flow regimes can lead to more stable and efficient designs in microfluidics device, drug delivery systems, and emulsion processing. So, in conclusions, viscosity plays a critical role in flow pattern formations. Higher oil contents and therefore higher viscosity reduces the diversity of flow patterns. The flow patterns maps developed here can aid in the design and optimization of two-phase flow systems in miniaturized applications. Ladies and gentlemen, this study was supported by the Department of Mechanical Engineering, Universitas Muhammadiyah, Yogyakarta. We extend our sincere gratitude to all contributors, technicians, and colleagues who helped make this research possible. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.